Hello, I Anand Jain from Hanumangarh, Rajasthan welcomes you to Shridevi Classes YouTube channel where we inculcate interest and confidence in science and engineering subjects. Today in our class 12 senior secondary physics playlist in our chapter electromagnetism, we'll start application of Biot Savart Law, and in the series of two learning video, in the first learning video, we'll explain probable board, NEET and JEE examination questions. The friendly explanation enriched with experience and dedication will not only improve your subject understanding, will clear all your doubt and help you to score more in your examination. Let's start. Two scientists, Biot and Savart, has given relation for elemental magnetic flux density contribution from a current element length, and according to Biot Savart law, a small length carrying I current produce a elemental magnetic flux density contribution at observation point P, which is at a distance r from current element, and position makes an angle theta with current element as shown here, and magnetic contribution is mu 0.4 pi vector product of current element and unit position vector divided by square of the distance of observation point from current element. The vector product of two vector is magnitude of first vector, second vector is unity in magnitude, and sign of the angle between current element and position vector, that is sin theta, and the direction of magnetic flux density contribution is obtained by vector product rule from right hand corkscrew rule, which says that vector product of current element and position vector is normal to the plane which contain current element and position vector, and its direction normal to this yellow highlighted screen plane is given by progress of this screw in cork when it is rotated from first current element length vector to position vector by small angle, and this rotation will make its inward progress perpendicular to this yellow screen as denoted by this cross symbol here. The direction of elemental magnetic flux density can also be obtained by right hand thumb rule, and according to which when conductor is gripped in right hand with thumb pointing the direction of current, then the curl of finger around conductor represent concentric circles of magnetic field, and according to this tip of finger at this observation position indicate inward direction of magnetic flux. To obtain magnetic field contribution of a longer length, we do little mathematical manipulation and convert these three variable length, distance and angle between current element and position vector theta into a single variable theta, and by integration we can obtain resultant magnetic field of a straight current carrying conductor. The magnetic field of straight AB conductor carrying I current is given by this relation. Here this capital R is perpendicular distance of observation position from conductor, and these two theta 1 dash and theta 2 are inner angles made between current element length and distance vector connecting extreme ends of conductor to observation point. Now the same result in terms of angle between position vector and perpendicular vector alpha 1 and alpha 2 is given in terms of sine alpha 2 plus sine alpha 1, and our result is in terms of theta it is mu 0 I upon 4 pi r cos theta 2 plus cos theta 1 dash, and in terms of alpha 1 and alpha 2 it is mu 0 I upon 4 pi r sine alpha 2 plus sine alpha 1. And if this conductor is infinite and observation point is middle point, then both theta 2 and theta 1 dash become 0 and alpha 1 and alpha 2 become 90, and our resultant magnetic field will become mu 0 I upon 2 pi r Tesla at observation point P, which is midway of infinite length. And if observation point is at one extreme end, then one inner theta angle theta 1 dash becomes 0, other one will become 90. One alpha 1 become 90 and other alpha 2 become 0, and in that case out of these two parameter one is 1 and other one is 0, and resultant magnetic field is half of mid value mu 0 I upon 4 pi r Tesla. To find out direction of magnetic field of this straight current carrying AB length carrying current I in upward direction in this screen plane, as per Maxwell right hand thumb rule, conductor is gripped in right hand with thumb pointing the direction of current, then this curl of finger around this conductor represent the direction of magnetic field. In front of this conductor the magnetic field is directed in this blue arrow direction, whereas to the back side the direction of magnetic field is given by this arrow. Now to the right side of this conductor, the curl of finger indicates that this tip of finger at this position is going inward and direction of magnetic field is inward, denoted by cross. And to left of this conductor, the curl of finger indicates that the tip here will indicate a direction outward as denoted by dot. So to right of this conductor, magnetic field is inward, and to left of it, magnetic field is outward. Let us start our applications of Biot Savart law from a simple textbook problem. We have given a conductor of L length carrying I current, and we have to find out magnetic field flux density at its central position at a perpendicular distance L by 4 from it at point P. We know for a finite length, magnetic field flux density of a straight conductor is given by this yellow highlighted result, where R is perpendicular distance of observation point from conductor, and this is L by 4 given to us. And due to symmetry, as this observation point is at central position, the two extreme theta angles, angle between current element and position vector, theta 1 dash and theta 2 in our case, become theta each, and the summation become 2 cos theta, and cos theta is in this triangle base upon hypotenuse. Base is half of conductor length L by 2, and hypotenuse is base square and perpendicular square rooted from Pythagoras. Now this L and the 2 get cancel out, and when we brought L by 4 common, this L by 2 is 2 times of L by 4. So our Pythagoras calculation become root 5. This 4 in numerator makes our result 4 times mu 0 I upon root 5 pi L in Tesla unit become our magnetic field flux density at observation position P. As far as direction is concerned, we can find out this direction of magnetic flux density of straight conductor by right hand thumb rule. According to this rule, conductor is gripped in right hand with thumb pointing the direction of current. Then the curl of finger around conductor represent concentric circle of magnetic field, and this circular shape directly indicate that the tip of finger at this observation position goes inward as shown by this cross here. In sum of symmetrical current distribution, resultant magnetic field flux density at our observation position will become 0, as oppositely placed sides carry identical amount of current in the same direction, and they produce equal and opposite magnetic field to nullify each other. Or there may be some straight current sections for which our observation point become an axial point for those straight conductor, and a straight conductor won't produce any magnetic field along its own axis. So these straight sections won't produce any magnetic field, and these two opposite placed side carry identical amount of current in the same direction and produce resultant magnetic field 0 at this observation position. As this can be explained by Maxwell right hand rule, this total current I divide in two equal sections I by 2 and circulate as shown in this figure. And for these two opposite sides, when we apply Maxwell right hand thumb rule, the thumb is pointing in the direction of current, then this curl of finger shows concentric circle magnetic field, and this tip of finger at observation position indicate a cross or inward direction of magnetic field from this conductor's current side, whereas this opposite place side also carry current in the same direction of same magnitude, and observation position is symmetrically midway of the two, and this will produce magnetic field. When thumb is along direction of current, the curl of finger indicate outward magnetic field perpendicular to this plane, and the two magnetic field equal and opposite cancel each other. Likewise, these two opposite place side also carry same amount of current in the same direction. So for at symmetrical mid position, the resultant magnetic field becomes 0. Likewise, in this cube, for this center of cube position, this incoming current and outgoing straight current got axial position of observation point, so they won't produce any magnetic field on this observation position, and the current divide in 3 parts at 3 sections, and then each current divide in 2 parallel sections, and division of current and flow of current is shown in this diagram. Now these two opposite place sides have identical amount of current in the same direction, and observation point got symmetry, so two magnetic field equal and opposite cancel each other. Likewise, this get cancelled by this side will get cancelled by this side, and this side will cancel by that opposite place side. So all sides got a symmetrical opposite place side carrying current of same magnitude in the same direction, and for symmetrical middle position, two opposite place sides produce equivalent opposite magnetic field to nullify each other effect, and resultant magnetic field at this center position becomes zero. For this center point of equilateral triangle, these two straight lengths got this point on their axis. So these two straight current carrying length won't produce any magnetic field along their axis. And these two current forming a sort of enclosure for this point add with each other, and as per Maxwell right hand thumb rule, when thumb is pointing in the direction of current, then this tip of curled finger at observation position indicate inward magnetic field for both these currents, whereas right hand rule for this current shows outward magnetic field at this observation position. So the two will act against each other, and this smaller section got double current, so it will produce magnetic field equal to sum total magnetic field of these two current length, and resultant magnetic field becomes zero here. We can understand this current distribution at these two positions. This single length resistance and this double resistance are in parallel, and current will divide in the inverse ratio of resistance. So smaller half resistance will have double current, and sum total of magnetic field of these two will get cancelled by opposite magnetic field of this current section, and resultant magnetic field at this center position will become zero. We have given two straight infinite parallel conductor carrying current I1 and I2 perpendicular to this yellow highlighted screen as shown in this figure, and we have to find out resultant magnetic field from these two currents on joining line at middle position P and to the right of right conductor at position Q. Since magnetic field flux density is a vector, so we have to first find out the direction of magnetic field from I1 conductor at P and Q, and similarly from I2 conductor at P and Q. If two magnetic fields are in the same direction, then their vector summation become a simple summation, and if two vectors are just in opposite direction, then the vector summation become a simple difference of the two magnitudes in the direction of bigger magnitude. To find out direction of magnetic field by I1 current at position P, we first consider a plane of current length and position vector, and our resultant magnetic field must be perpendicular to that plane. And to check whether it is in this perpendicular direction, we can use Maxwell right hand thumb rule. When thumb is pointing in the direction of current, then this curl of finger represent concentric circle of magnetic field, and this tip of finger here perpendicular to this plane of current and position vector indicate this direction of magnetic field as by this arrow. Similarly, for Q position, this I1 current produce magnetic field B1 dash in the same direction, in upward direction. To find out direction of magnetic field from I2 current at position P and position Q, once again we generate a plane carrying I2 current and position vector, and our magnetic field must be perpendicular to that plane, and it is either perpendicular to downside or upside. That can be checked by Maxwell right hand thumb rule. When thumb is pointing the direction of current, this curl of finger here around this conductor represent arrow upward for Q position magnetic field of I2 current, and downward for P position magnetic field of I2 current. So for this parallel identical directed current distribution for middle positions, two magnetic contribution of I1 current B1 and I2 current B2 are just opposite to each other, whereas at Q position right of right conductor, the two magnetic contribution of I1 current and I2 current are in the same direction. So at P, resultant magnetic field is either a difference B1 minus B2 or B2 minus B1 depending upon which magnitude is bigger, where B1 magnetic field of I1 current at R1 distance for infinite conductor at mid position is given as mu 0 I upon 2 pi R1, and similarly B2 magnetic field of I2 current at R2 perpendicular distance for infinite length conductor at mid position is mu 0 I 2 upon 2 pi R2. Depending upon magnitude of two currents and two distances, we can find out the magnitude of B1 and B2, and the difference of the two will become resultant, and resultant magnetic field is directed in the bigger magnitude direction. So for position very close to I1, resultant magnetic field is in upward direction, and for position very close to I2 current, B2 magnitude being higher in magnitude will produce resultant magnetic field in downward direction, and there could be a position in between the two conductor on joining line where the two magnitude become equal and opposite, and resultant magnetic field will become 0. Now for Q point, the two magnetic field are in the same direction, so resultant magnetic field is summation of the two, where B1 dash is magnetic field of I1 current at this R1 dash distance, mu 0 I1 upon 2 pi R1 dash, and similarly this is distance of Q point from I2 current R2 dash, and its magnetic field is mu 0 I2 upon 2 pi R2 dash, and the summation of 2 is our resultant magnetic field at Q. Just like previous case, we have two straight infinite parallel conductor, but we have changed the direction of current of I2 current. Earlier the two current are in the same direction, now these two parallel current are in opposite direction, and we have to find out resultant magnetic field on joining line at middle position, somewhere in mid of the two at P, and to right of right conductor at Q. Once again, let's first find out the direction of magnetic field contribution by the two currents at position P and position Q, and we know the direction of magnetic field is perpendicular to the plane which contain current and distance vector, and it is perpendicular to this yellow highlighted plane, either upward or downward, depending upon the position indicated by right hand corkscrew rule or right hand thumb rule. And right hand thumb rule is convenient in approach. When the conductor is gripped in right hand with thumb pointing the direction of current, then this curl of finger indicate concentric circle of magnetic field, and this circle indicates that this I1 current, denoted by dot perpendicular to this screen plane and outward, will produce magnetic field in upward direction at P and at Q. Whereas for I2 current, the direction of magnetic field is perpendicular to the plane which contain current and the distance vector, and it is either in upward direction or downward direction given by right hand thumb rule. And when current is inward, then this curl of finger represent direction of magnetic field which is upward at position P and downward at position Q, as clear from this diagram. So at observation position P, magnetic field of I1 and magnetic field of I2 both are in the same direction, and resultant magnetic field will become the sum of two. And for infinite length conductor at mid positions of current I1 and distance R1, magnetic field is mu 0 I1 upon 2 pi R1, and similarly for I2 current at R2 distance, magnetic field is mu 0 I2 upon 2 pi R2, and at P position resultant magnetic field is simple summation of B1 and B2 in upward direction. Whereas for Q point, the magnetic field of I1 current at Q position is at upward direction, but for I2, this clockwise circle represent a downward direction at Q position, and resultant magnetic field is difference of either B1 dash minus B2 dash or B2 dash minus B1 dash, depending upon which one is higher in magnitude, and the magnitude depends upon magnitude of current and distance. Now for I1 current, the distance of observation position is R1 dash, and for I2 current the distance is R2 dash, and two magnitude can be obtained and the difference can be obtained as resultant magnetic field. In an iron core of relative permeability 1000, we have embedded two infinite parallel conductor carrying current I1 and I2 in opposite direction. Each current is 10 ampere. The spacing between two conductor is 0.1 meter, and we have to find out resultant magnetic field to the right of right conductor at 0.1 meter distance. That means this observation position Q is at 0.2 meter distance from first conductor. Now this dot current perpendicular to this yellow highlighted screen plane and in upward direction produce a resultant magnetic field in anti-clockwise direction, and its contribution at Q point B1 is in upward direction, and this I2 current inward in direction produce a clockwise magnetic field around it, and its contribution at position Q is B2 in downward direction. Since this I2 current is closer to this Q position, so with same amount of current, the magnetic contribution of I2 current B2 is higher than B1, so the difference is B2 minus B1 in downward direction given by this relation and the current of 2 is 10 ampere. The distance of nearer conductor is 0.1 meter and far away conductor is 0.2 meter, and mu 0 upon 2 pi, when mu 0 is taken as 4 pi into 10 to the power 7, become 2 into 10 to the power minus 7. Mu r is given 1000. Now this 10 divided by 0.1 is 100, 10 divided by 0.2 is 50. The difference is 50. 50 multiplied by 2 become 100. 100 and 1000 become 10 to the power 5. And with 10 to the power minus 7, it become 10 to the power minus 2 or 0.01 Tesla value. So in this informative learning video, we have explained some typical application of Biot Savart law usually asked in our examination. The practice of these example will definitely enhance your subject understanding and scoring ability. Our other learning video of same senior secondary physics playlist are equally useful in your studies, and if you need our online doubt clearing classes and dedicated exams and trick notes, do join our YouTube membership by clicking join button just beneath, and by a little investment we will help you to improve your exam success. Happy learning. Thank you very much.